topics. Welcome to Modern Application Development Online Event. Today we're going to go through 3 topics. Moving from a monolith to a microservice, and how would you deploy on modern technologies such as containers, event-driven systems, and orchestration. My colleague Gabe Hollenbay is going to talk through how to build orchestration and workflow using AWS step functions, a managed state machine. And finally, Matt Fitzgerald, Principal Evangelist, is going to talk through how to use Event Bus and eventing systems to be able to build messaging systems so that you can scale your microservices. So join us on these 3 talks today, and we'll talk you through building a modern application deployment. Hi, and welcome to Modern Application Design. This is Building Effective Services with Shaun Ray. I'm Senior Manager for Developer Evangelism in AWS. And today I'll be talking through the business cases and how we build a modern application. So in the agenda, we have the business case. So why are businesses actually building modern applications? Why do your business people care about the fact you're building modern applications? We're going to talk through the 3 common architecture patterns: monoliths and microservices, event-driven systems, and workflow orchestration. And my colleagues after me, so Matt and Gabe, are going to talk through these last 2 architectures in great detail. On number 3, we're going to talk through the operating model. So once you have moved to microservices, there's a whole bunch of operational considerations you need to do. So how do you deploy? What's the right abstraction? And how do you monitor everything once you've deployed that? And finally, we're going to talk through software delivery. Now that we're in an age of microservices where things have their own deployment pipelines, how do we effectively manage those hundreds of microservices at scale? So the business case for modern applications is really driven actually by your end customers, by the business that your company is in. And it's not necessarily driven by IT projects. CIOs and CEOs are being told by their boards that they need to do digital transformation. And Gartner has done surveys and found that 47% of CEOs are being told that they have to change their business from their board. 79% of CIOs are saying that they need to actually do digital transformation to be effective in their business. And 67% of all business leaders believe they must up the pace of digitization to remain competitive. So there are pressures coming from the business as you as IT people are going to serve. And that means that we need to build our applications in more agile ways and more cost-effective ways so that we can actually address those concerns from the business. And the way that we think about this and the way that we remain competitive is the innovation flywheel. So the idea is that we take something that is not too risky and we experiment with it. We build a small piece of code or an application and we show that it returns value. So we don't go out and do a multi-year project. We don't go out and spend $100 million. We do something small, something that's critical to the business, and we experiment with it. From that, we get feedback. Was it successful? Did we measure the right things? And then we use those ideas to scale through the business again. So now, instead of doing 1 application, we're doing 50, or we're building a whole new interface to our mobile application. So we want to start with a small experiment, show value, and then scale it through the business. And some of our customers have already been on the modern application development journey. So FICO, they reduced their overall compute cost by 95% by moving to a serverless orchestration platform. The Coca-Cola company, they cut their processing time from 36 hours to 10 seconds for putting the nutrition labels onto their cans. And FINRA, which is a financial regulator in the US, they built a stock trade validation system in just 3 months, whereas previously it was taking them over a year. The Washington Post newspaper publication, they are now doing 50 deployments per hour. So they have a huge velocity in putting out changes to their business. And this is part of that innovation flywheel that we just talked about, where you want to experiment and then move up the cycle. So they wouldn't have started at 50 deployments per hour. They would have started at some other number and then optimized until they got there. And so what defines a modern application? What does this term actually mean? What we've found from our millions of customers that are on the AWS platform is that they're generally built on containers and serverless. They've generally gone for a microservices architecture and they're distributed in nature. Each component is autonomous and independent, meaning that you can deploy it separately. You don't have to wait to deploy other applications. And finally, you can actually monitor those applications. So things like distributed tracing and open monitoring, so that we can understand that when someone does a user request from the front end all the way through the database, we can actually see what's going on for the total performance of the application. So how do we actually get there? If we're in the current world and we have been told that we need to innovate, our CEO and our CIO are telling us to, what do we actually need to change as IT practitioners to be able to build a modern application? So the three things we need to look at today are architectural patterns, how are people building these applications, what the operating model is, what cultural changes, what operating changes do we need to make so that we can actually run these applications, and finally, what do we need to change in our software development practices, either with our developers or with our DevOps practice if we have one of those set up. If we look at the architectural patterns that are very common at the moment, most people start with a monolith. And the reason that you start with a monolith is you need to understand what your business is. And so some companies have been around for many decades and they have a huge monolith that they have one big deployment artifact and they put it into production. And sometimes that means that the releases are much slower. But Martin Fowler, who writes extensively about microservices and monoliths, says that you should start with the monolith first. If you're a brand new company or you're setting up a brand new division, you might not necessarily know what the boundaries are for you to break something into a microservice. So building the monolith is actually a good way for you to understand the business problem. And on the other side, we have microservices. So the monolith does everything, and everything is contained in that one package. In the microservices side, we start to build different services for different interactivity. It's probably easier if I display it a little differently. If you think about the monolith generally has one package, so a jar file or your type of application file. It normally has a shared database. So you're having one database with everything managed. So accounts, users, reporting, all in that one database. It quite often has a shared interface. So you might have an API, but the API does users and accounts and payments and reporting. It has shared logging. So one nice thing about a monolith is generally the logging is all in one place. So you don't need to worry about distributed tracing and other types of operational concerns you have when you go to a microservice. And it has a single deployment. So if you know how to deploy the monolith, then you can deploy all the packages at once. On the microservices side, we have it a little bit differently. We do have our application code for that microservice, but it is only doing that one thing. It's only the user concern or the account concern. We have a data store, and different to the monolith, we generally have a data store per microservice. So the microservice that owns a particular piece of data, it might own user accounts or it might own billing. It actually owns its own database. And other services do not talk to that database without going through the public interface of that microservice. It has a custom interface. Because it has a custom interface, say on payments, then you can actually build specific functionality for payments, such as batch payment or reporting, without having to worry what the rest of the interface is doing. It has its own logging. And often when you get to 100 microservices, you start to realize that you've got a lot of different login patterns. And so you start to standardize. So you won't have the standardized login that you get out of a monolith. And finally, it has its own deployment logic. It's very common that when you move to microservices, there's different teams who are in different services. And so what happens is that they have their own deployment logic. One team might be writing in Go, another team's writing in Java, another team might be writing in PHP. And so they will have different ways for you to deploy that service. And so you start to end up with different deployment logic. So it's nice and loosely coupled, meaning that they can deploy independently. However, if you're the ops person and you have to deploy these three microservices, you now have three different ways of doing it. And if you look at those architecture choices and the design patterns we were talking about before, then you can see on the left-hand side that the monolithic architecture has the UI, the business logic, and the data access layer all kind of contained in that one package. And then they'll generally have their shared data store. And on the right hand, we have our user interface, which could be your JavaScript or your native application. And then we have our microservices underneath. And each of them have their own messaging patterns. And so we have to be aware that some microservices don't talk to the UI, and some don't actually talk to the databases. Some microservices only talk to other microservices. And so to build out the architecture and to draw that architecture out becomes a little bit more complicated. But it does mean that if accounts is way more busy than payments, we can scale it separately. And in the monolith, you can't do that. You have to scale the monolith up or across for all components, which means that you normally have utilization where one part is really busy and one part is really slow. And so you're not utilizing your resources well. And what a microservice architecture looks like. So a common pattern is that you'll have your clients, which we have on the left here. They could be mobile or IoT or the actual web client, and they're coming into a front-end API. And generally the way that you access microservices is through an API. So this might be a REST API with JSON, it might be some kind of gRPC API. And then the microservice will do certain things with that data. It might go off to a persistence data store, it might talk to another microservice, or it might emit an event in an event-driven system. And this is actually the same interaction that you'd be getting out of a monolith, except that the microservices is just doing its one thing and doing it well, built on the Unix philosophy. And as we go through that architecture, you'll start to see some common patterns. So if we map that to a business, you'll see that we have a consolidated API gateway up in the left. And this means that it might be a managed service. And the reason that people choose a managed service for API gateways or they create their own is because there's certain things you need to do once you start having a public-facing API. You might need to do rate limiting. You might need to have access keys, so only certain people can get to certain parts of your API. And so instead of managing that at each microservice level, companies often choose to actually use a managed API gateway so that they can consolidate those types of access patterns. We have our little microservices here in the blue honeycomb icons, and then we have our databases at the back. So this is for an e-commerce application. So you can see we have the store web front end, we have inventory query, we have shipping, when's it going to ship, we have an account lookup so that we can authorize you, and then they each have their own databases. And you'll see there that account lookup and shipping query actually talk directly to each other without a user interaction. And so you'll start to see that microservices don't necessarily need to have public interaction to start doing things. And this is a common business use case. Any of the companies that are out using Drupal and other types of things for e-commerce often have this type of setup. Once we have decided that we're going to go microservices or monolith, we have to be able to deploy that application somewhere. And so I'm going to take you through a little bit of history about what the deployment options are and then what the trade-offs are of each of them. So if we start with physical servers in a data center, we can fit as many as we can fit into a rack with as much power as we have, and then they become our servers. So we can have 6 servers, they're physically constrained, and we can split them up. If it's a monolith and we're doing managed state and we don't have a load balancer, then realistically we can only use one of those servers and utilization might be low. Then came virtual servers. So these are your VMware and your Citrix Zen servers and other virtualized type servers. So now we didn't have to worry about the fact that we had CPU limitations or memory limitations on the host. We could start to do things like make test environments with 1 CPU and 1 gig of memory. And we could start to utilize the servers right up to capacity. But only to the point where we could actually say, right, this application actually needs 4 CPUs and 10 gigabytes of memory. If it ever only used 1 gigabyte of memory and 4 gig, even though it had already been assigned to that VM, we couldn't really take it back away. So it meant that you had to be really good at understanding the capacity of your applications. And if you had peak time, that meant that you had issues where you needed to scale up really fast and you still might hit those physical limits. And then finally, since 2006, when AWS launched, we've had the cloud. So virtual servers in the cloud where you call an API, the provisioning time is a minute or so, and then you can have hundreds or thousands or 10,000s of these servers. And so the idea with cloud computing is that you get high utilization because you're only using servers when you need them. It means that you have faster provisioning speed. In my own experience, where I used to work before Amazon, it used to take us about 12 weeks to get a fully provisioned server that was on the internet, and now you can get one of those in 1 minute. You also get improved uptime because the vendor is actually managing the patching and the hardware and the failure of this and those types of things. It means you can use it for disaster recovery because now you can clone those particular applications and move them to other servers very quickly. And finally, you get hardware independence. You don't really care what the hardware underneath the actual virtual server is. That's a problem for the actual vendor. There are a couple of trade-offs when you move to the cloud. So one thing is, if your company is very used to spinning up a project and using capital expenditure to buy in servers, you're going to be switching to an OpEx model. So you have to understand that you will need to talk to your accounting team, your finance team, and say, hey, we're going to have a line item every month about what we're going to spend on the cloud. You can't just allocate me a certain amount of money upfront in CapEx that I can draw down on. The other thing is you'll have more scale. So with more scale becomes more responsibility. If you have a new data science team who has some data and it currently takes them 12 hours to run, but they decide they want to run it in 1 hour, they can absolutely do that in the cloud by scaling up to more servers, but then it obviously increases the cost over that period. You can use elastic resources. So if you happen to be in a business where you have one big peak day, maybe a flash sale, you can scale all the way up, and the next day you can scale down, and you only pay for what you use. After the era of computers, we started to get into containers. And containers is a hot topic right now. And really what containers are is it's an immutable object that contains your code, the dependencies, and your runtime. And the reason they became popular is it allows us from a virtual server capacity standpoint to put 10 containers or 100 containers. And so we can get that utilization much higher than we can with a virtual server. It also means that the runtime is separate from the operating system. So if you deploy software that needs to deploy on Windows and Linux, or you want to test locally on your MacBook, you can now do that with containers like Docker containers because you are abstracting the operating system away from your actual code. And so that made containers very popular. It means that you can local test things like microservices where you might have a whole bunch of dependencies that you need to rely on, and they're nicely baked into that container. And so after you've chosen whether you're going to go virtual servers or not, you'll most likely choose whether you want to go containers or not on top of that. Containers are excellent for stateless applications, applications that need lots and lots of horizontal scaling. They're generally still in kind of immature states depending on the networking for whether you want to run databases and different things in containers in production, but they're great for local testing and getting your developers enabled across different fleets. And then we have one other evolution at the end of this computing journey, which is serverless. And serverless came from physical data centers where we wanted more utilization. Then we went to virtual servers where we needed more utilization again, and we could make smaller increments, but we still had to guess what the capacity of our application was. We went into virtual servers, and maybe virtual servers with containers. And with containers, you are still building an immutable object. So it may last 1 minute, 1 hour, 1 year. It just depends on how often you actually update that software. And with serverless, there was a push to, what if we just wanted to run a function? And we didn't know if we needed to run it once or 1,000,000 times or 100,000 times a second. What if I just want to build my code? Because with containers, you still need to understand the network and subnetting and the capacity requirements. And so serverless was born. One of the first serverless products was called AWS Lambda, and it's a function as a service. And now all the major cloud providers have a function as a service that you can use publicly. And it allows you to do things like run code in 100 millisecond increments, and you can run it once or you can run it hundreds of times a second. And the idea is that you only focus on your application. You can couple that with things like the simple notification service, which allows you to do publish and subscribe. So you may, for instance, have one notification that needs to go out, or maybe go out to 100,000 Apple phones or Samsung phones or whichever phones that you're providing. And you can use a Lambda function to trigger that notification, and it will go and talk to your 10,000 subscribers on the other end and push them a notification. We have step functions, which Gabe Hollenbein, my counterpart, is going to talk about later on today. And that is a state manager. So instead of having microservices that talk to each other and nothing orchestrating them, you can also manage the state on the way through. So for instance, if someone needs to delete an account and you need to reverse a payment, then step functions will allow you to manage that state so that you can understand that you reverse the payment and now you can delete the account or like disable that account. We have queuing services. So you might want to put things on queues so that readers, a Lambda function in this case, or a container can say, hey, there's 100 jobs on the queue. I'm going to read from there. and I'm going to drag that number down and process them. And then we have API gateways, which we talked about a little bit before, where you have a managed gateway so that you can do things like caching, you can do things like authentication. So APIs are really the front door of microservices. And when you choose to do microservices, you're going to have to find a way to build an interface and a contract with your downstream consumers. So this might be that the application team or the native team needs to build iOS hooks so that they can talk to your API. It might mean that another microservice depends on your API. And you have some design choices around what you want to do there. So that is whether you want to go with things like HTTP and JSON REST, which is very common, whether you want to do something like a binary format or gRPC, and so that you can get much more volume across the wire because people aren't interacting with that API. And so you want to make sure that your API is clean, that it's idiomatic, and that you can use it in a way that is self-explanatory. So if you have a user API, then you can use a post to create a user, and you can use a read to read a user. And you can create an API that when you look at what the name of the API is, it's quite intuitive for people to use. And so you'll need to make some choices around what technology you use there. And if we look at what an API looks like, you'll see that the full kind of implementation of microservices has a few other components. So we don't just have an API hitting the front end. We generally have something like a Amazon CloudFront, which is a content delivery network. If we're sending out lots of pictures or heavy multimedia, we want that content delivery network to be able to cache those files so closer to the user so that we don't have to go back and hit the microservices every time. So we get improved latency. We want to have API endpoints that have caching so that means when a request comes in, maybe query to a database or some other type of service that we've already gone and talked to multiple microservices to get, we can actually just read from the cache if it's not too old. We want to look at things like monitoring. So we might want to see all the requests that are coming in the front door, regardless of what microservice they're going to. What's the latency coming through there? How many errors are we getting? So it gives you a nice, easy point to be able to concatenate those business metrics and then report them back. Once we get through the kind of microservices with APIs, we move into things like event-driven architecture. So this is a different way to think about traditional microservices where you might be used to doing the HTTP REST JSON APIs. So microservice message patterns and where eventing comes from is you might need to send an event you don't care about. So you might just broadcast it out, someone reads it from a queue, and then you don't really know what happens with it. There's other messaging patterns like request response. You send a message, you will wait for the response to actually come back from the person you're sending it to. You have things like return address, where you are providing an address that then the third party actually sends you back a response to, so like a callback. And you're trying to, in these states, decouple the fact that your microservice needs to talk to another one. So you're generally using queues in between, and you are pushing messages and events around. So if my microservice emits an event, then I don't necessarily care who's reading it. They might subscribe to my event and read it, but I don't give them any SLA about what to do with that event. It is the team who owns that microservice who processes that event that cares about what's in that event. So with something like publish subscribe, then that is done on a much larger scale where you might have one consumer or 10,000 consumers consuming your event, and they take action based on that event. So it means that I don't need to know the API of that particular microservice. I don't need to come through the front door. I'm just listening for that event. And so when you have very busy services, or you might have a user service or an account service that all other microservices need to talk to, it means that they can just emit events when accounts are created or accounts are closed or accounts hit 30 days and you want to send them some type of marketing message. They don't need to understand everyone else who consumes them downstream. As long as they keep producing events, that means that your microservice can process them independently. We also need to be able to manage the state of our applications. If we're not using event-driven systems, then we need to be able to figure out what actually happens in failure scenarios. If I'm the API gateway and I send it to a microservice that's processing an order, and I click on there and it says, actually, we are out of stock on this item. and I've gone to 2 other microservices to get that. Now I need to cancel the order and say in the front end that you can't actually progress, or I need to remove that from your cart. And so we need to be able to process those type of requests, and we also need to be able to process failures. The CTO of Amazon, Werner Vogel, says that everything fails all the time, and we need to be prepared for that. It might be that your microservice calls another service and it's not there. It might not even be in your control in your company. Generally for payments, for instance, people go to things like credit card gateways to make payments. So you might not even be in control of that third party that has failed or has slowed down and is now causing your users issues. And so we need to understand what the sequence of tasks is. We need to understand what the dependencies on all the other downstream services are. And so the way that we do that is we try and manage state. And we need to be able to do things like retries. We need to be able to do things like try, catch, finally. Or we want to do decision trees on if this service fails, try this backup service. Or if this service doesn't give me the event I want, then I need to go and do X task. And the way that we normally do that is with managing state through something like AWS step functions in a state machine. So AWS step functions allows you to call out different compute and kind of process workers. So this might be an AWS Lambda function. It might be something sitting on EC2, a virtual machine, or it might be some other type of database or something that's natively integrated. You might be putting a message on a queue. And it allows you not to just do single execution tasks, but parallel tasks. And Gabe's going to talk through great detail how you can actually orchestrate these types of events. He's going to show you details on the different types of processes that you can use and the workflow decisions that you can manage. So I'm not going to go too far into it in this talk. We also have a couple of other things that happened in step functions, which are serverless polling. So you can now be able to poll for work out of serverless, meaning that you can do things like asynchronous calls and you can just poll back when something actually finishes. And so while this is a native part of step functions, it means that we can start to do things like decouple our microservices with callbacks instead of waiting specifically for a function to change. We also now have built-in functions so that you, without having to use Lambda, can start to do things like synchronous calls or run a batch API with our batch system where you can run a HPC workload, for instance. And so that's something to keep in mind when you're designing these systems, not just to use step functions for things like serverless and containers, but also you can start to call heavy compute. So in summary of a modern application, cloud native architectures are small pieces loosely joined. They do one thing in the Unix philosophy, and you can either use event-driven or API-driven to choose how tightly you want to couple them to your downstream systems. Now that we have just decided our architecture, we need to understand how to operate this different type of software. If you look at the left-hand picture and you just look at that kind of logical representation of the microservices, you can't really see what's talking to what depends on what, and how do we operate all those different pieces. So there's some operational responsibility when you start to use the cloud. No more do you own the physical server and the cabling in the data center. And depending on where you go on the compute spectrum between bare metal, virtual servers, containers, and something like a function as a service, there's different ownership models. You're not operationally in control of all those different pieces. At one end, in the bare metal, you're responsible for everything from the hypervisor up. And on the other side in AWS Lambda, you only really care about your application code, and all the other things like operation and security and patching are all taken care of by the vendor. So this graph shows what the operational matrix is and responsibility is for AWS services. And if you're building these on your own internal services or using other third-party applications, I kind of encourage you to draw out something like this so you can understand what you own and what everyone else owns. So we talked a little bit about serverless before. On the operational model, it means that there's no infrastructure provisioning at all. You just write your application code, you upload it to your cloud provider, and then there is no management. It just runs in response to events. It has automatic scaling, so you can set it to do 100 or 1,000 or 10,000 invocations at the same time, and you pay for value. In AWS's Lambda case, you're only paying for 100 millisecond increments, and is highly available and secure. it's AWS's job to patch Lambda, to patch the runtimes, and to make sure that it's secure when you run your code. And if you look at the span of those different types of service, you have Lambda in compute and AWS Fargate. We haven't talked about Fargate before. Fargate is a managed way to run containers where you can care less about the infrastructure. So you don't have to worry about running the orchestrator. You don't have to worry about running the master node and understanding the different tasks that you need to do. Fargate extracts one layer up, so one layer down probably from AWS Lambda, where Lambda, you only care about application code. Fargate, you still do care about what's the kind of capacity that I need to build in for this particular function, but it's fully managed on containers. We have our managed data stores, so AWS S3, so an object data store that allows you to just call an API, put your objects, draw them back out, and it's completely managed by us. You can put trillions of objects into that data store, you can draw out hundreds of gigs, and we manage that capacity for you. Amazon Aurora Serverless is a managed database that is MySQL and Postgres compatible, and it allows you to use a relational database in a completely serverless way. So you don't need to worry about connection pooling and building proxies so that you can talk to things like function as a service. And finally, we have Amazon DynamoDB, one of our oldest databases that allows you to use NoSQL in a fully managed way without provisioning capacity. Then we have the integration services, and we've talked through those, and my colleagues will be talking through those in more depth, so I'll leave them to do that. So on the responsibility side, we need to understand what we're actually managing ourselves. So this map shows you exactly what AWS manages and what the customer manages. So on the extreme, you have AWS Lambda, where you have the app code, and on EC2, we do the physical hardware and software, and then you do everything else. So depending on your application, you can kind of decide with this decision matrix how far up or down this decision tree you would like to go. So in our modern application, we have gateways, we have things like EC2, and we have Lambda. And in an operational sense, the team that runs the API gateway might be different from the team that runs the application on EC2, and it might be different from the team that is running something on Kubernetes down on the end there, or AWS Lambda. But the business doesn't really care about that. If I'm a user, I hit your website, I hit your mobile application, I try and do something, I want it to be fast and I want to get it back so that I don't have any errors. And so how do you actually tie all of those different components together? And the way that people are more commonly doing that now is called distributed tracing. So in this case, we want to be able to trace from the user journey when it hits our on-premise front end all the way through till we get the response back from the database. And we want to see actually what that means. And the way that we do that is called segmenting. So the front end on-premise interface that we might not have migrated to the cloud yet has its own segment. The gateway has its segment, and then each component has its own segment. And so that means that we can say EC2 took 15 milliseconds and had this error response rate, and on-premise took this many milliseconds and had this response rate. So we can tie all of those together into one trace and see what actually is happening for that user. We also have something called sub-segments in open tracing. And this is where in distributed tracing, and this is where we want to understand the path of a particular system that is completely outside of our service. So something like DynamoDB, where we're relying on a third party and we care about that interaction, and it sort of spans different services. So we want to be able to record a sub-segment so that we can understand what the database is actually doing specifically. And we're going to dive into one of those use cases to see how important that is. So AWS has a distributed tracing system called Amazon X-Ray, or AWS X-Ray. And this picture you're seeing is actually a real-life customer view of X-Ray, and they're showing all of their different services here. So there's Amazon S3 on there, there's some microservices that they've built, and the green dot is basically, the green circle represents how many errors. And you'll see that up in the top kind of left, there is actually one that has 1% errors, but it also shows things like average response time. And so through this, you can start to see how complex managing microservices are if you don't have access to monitoring where you can go end to end. And we talked a little bit before about the database. So it's quite often people build monitoring systems that hit the front end of the microservice. And they don't account for the fact that they're running SQL queries in the background or hitting a NoSQL database. And if we actually use subsegments like we showed in our picture, we can start to do things like understand that we're running an execute query here in this subsegment, and it's taking 12 seconds, and everything else is taking milliseconds. So we have something that's 10 times the order of magnitude worse than what most of our customers are getting. And so we need to understand, why is that one query taking 12 seconds? And because we've actually used subsegments here on our tracing, we can start to see the big problem. We can also start to add metadata to our distributed tracing. So we can add the actual SQL query to the metadata of the X-ray trace. So here you can actually see the specific update call that they're making to the database, which is causing that 12-second issue. So by using this type of access, we can start to see end-to-end what's happening through our microservice. So we can use trace IDs, we can use the AWS X-ray APIs like we're doing here to actually pull out in batch the trace and everything that it touches on the way through. So we might be interested in the user journey, and here we can see every single activity that that user is doing that's generating this 12-second problem. And this particular customer who spoke at reInvent last year actually uncovered that they had an issue not with their database, but with the way that they were calling their actual application. So they were using synchronous calls to send a whole bunch of messages. And each of those synchronous calls was waiting on the downstream message. And all of those calls were hitting the same database with the same query, causing that 12-second problem. And so by using distributed tracing and AWS X-ray, they were able to see an actual flaw in their implementation. So then they changed it to asynchronous calls, where they were just waiting for callbacks. And that 12-second layer that they were dealing with is now down to milliseconds, single-digit milliseconds, because they're now doing asynchronous calls. And so that has had a huge impact on their actual business metrics and the user experience for that particular query. The other thing that they did that was really smart was that they started to add things like member ID into their traces. So inside the HTTP context header, they could actually start to add different metrics in, like the company that that person was from, the member ID of that particular account. So not only could they trace on what is the overall service of that metrics, but what is actually that one user from particular company actually experiencing. And here you can see the response times for each of one of those users. And so if you have microservices where you need to understand, hey, this customer we have an SLA with, and in customer I mean big company, and there's these 5 users are having an issue, you'll be able to go down to that granularity if you start to use segmentation, subsections, and use the user annotations properly. And more importantly, the business cares about the actual metrics. So we can now see the percent of traces that these people or this particular type of query is using. So instead of having to go through and trawl our logs and do a report, we can quickly see that X% of our users, or 39% of our users, are creating tickets, and some are doing contact name. And so we can see the actual API queries. So now you have an operational view of what's happening in your business by using distributed tracing. And finally, we need to talk about the delivery of software. So now that we've made all of these changes, as we discussed in the opening with Monolith and Microservices, each of these microservices might have a different deployment pipeline. They might be running on different technology. And so how do we manage that from a software point of view? So we also need to think about serverless, because in serverless, we're not really deploying the code with infrastructure around it, and we don't really control much of the things because the managed platform, in this case, which is AWS, is controlling some of those things for us. So traditionally, the developers would build their application, they'd put it into their one big service, and this might mean that multiple people are working on the same code base, and then we put it through the delivery pipeline. And sometimes, and in my experience, we used to have a delivery pipeline in a regulated business where QA and testing would take 4 to 6 weeks to be able to test a piece of software before we could release it. And so if your very quick change that took you 1 hour, 1 day to make is now waiting 6 weeks to get into production, that can be quite frustrating for the business. And when we move to microservices, We want to change that. We want to make it so the delivery pipeline is completely independent for each microservice. And that means that we can then move down that pipeline as quickly as possible. We can deploy when our business needs and we don't have to wait on others. And what you do if you do have something that is dependent on a second microservice is you create a feature flag. And with that feature flag, you put it into production, you turn it off, and when this dependent microservice then deploys their piece of code, you flick that feature flag on and you start making those calls. So you can start to really decouple your delivery process from your dependencies. So what we've heard today from the best practices is you need to decompose for agility, you need to automate everything, you need to use standardized tools, and you need a belt and suspenders approach. So when you're doing things like security, make sure that you do things like static code analysis. Make sure that you do security scans as part of your pipeline, not afterwards where you're doing manual testing. And finally, you want to do infrastructure as code. So in that CI/CD pipeline, what it would look like is if you're using a full AWS stack, code commit, which is like GitHub, it's basically code. For build, you'd use code build. You could use third party for things like testing. And then for deploy, you'd use code deploy. So this is moving our application from I check in the code all the way to deployment. And finally, we talked about Amazon X-Ray for monitoring. And the last thing that I want to talk about, we just said in the best practices about infrastructure as code. So now that we have this fully kind of industrialized pipeline, we also want to think about the fact that we should have immutable infrastructure. So we can now do things like using Terraform, using CloudFormation. We can actually make our infrastructure code. And if we do that, then the infrastructure is now bundled with the application. And we don't have to worry about configuring, about building out the machine and then deploying our code. We actually deploy the machine or the container or the function as part of our code. And so now when we do versioning, we have a version of our application that contains the infrastructure. And one of the ways to do that is called the Cloud Development Kit, the CDK, and it uses constructs. It can also have third-party constructs, so you can use different plugins from different third-party vendors as well, so that you can start to make an immutable construct that contains all of your application. So just to reiterate, there are already some customers going on this modern application journey. We talked about FICO and reducing overall compute costs with optimization. The Coca-Cola company who went from 36 hours to 10 seconds by using serverless, and the financial regulator who deployed a full application in 3 months. And if you do the things that we've talked about in here, if you get those pipelines going and you start to build immutable infrastructure as code, you can get to where the Washington Post got to, which is over 50 deployments per hour. So rapidly changing your software. Where to go to learn more? OpenTelemetry is a Cloud Native Compute Foundation incubator project. It's just a merging of 2 other projects, so it's still kind of in the alpha stage, but looks very promising. We've heard several vendors who are going to take this on board. So if you go to opentelemetry.io, that is actually open source distributed tracing, much akin to what I've talked through here. Werner Vogels, our CTO, has done a blog post on modern applications and how people should think about them. And finally, modern application design by AWS. So this is a website that we've put together that puts most of these concepts, the different services, and the way we think about modern applications that you can go through there. So thank you for joining today. This has been an overview of modern applications. Coming up next, we have Gabe Hollenbay, who's going to talk through managing state and how to do workflow orchestration. And then after Gabe, we'll have Matt Fitzgerald, who's going to talk through event-driven systems and how you manage event buses. So thank you very much for joining today. If you're interested in any of these topics or you want to go further, we have training, which is specifically developing on AWS. So it goes through the concepts about how you do development on AWS and interact with some of these services I've been talking about. We have our Certified Developer Associate, if you'd like to get certified once you understand the platform. And finally, we have our DevOps Pro Engineer. So this is if you want to become a certified DevOps professional, you want to talk through building those pipelines like I've just gone through, then you can go and actually take that certification and show that you know AWS. After this talk, We're going to be whiteboarding, so Gabe and myself will whiteboard through some of these topics, so please join us for that after this. Thank you for attending Modern Application Development, our online event, and we'll see you next time.
Hey everyone, and thanks for staying with us. We just watched Shaun's excellent